All right, so how did the homework go? Good, bad, horrible?
Good.
Went all right?
Thought it was fun.
What's the purpose? It's supposed to be fun. It's kind of like you have to give a dog medicine. You hide it in the food. So you're learning about extended uses of data structures hidden inside of a video game. Unless you hate video games, you might not have found it as fun. But I guess it is what it is. Okay, so the idea here is we were supposed to create a collection of objects, including at least a room, a door, and a student. And then we need to create a way of representing the map of at least 15 rooms. And we'll start thinking through that. When a student enters a room, they should see the title of the room, the obvious doors leading out of the room, and any other inhabitants that might be in the room. Even though we're not putting things in there, that's kind of in preparation. We're going to have a list of things that are going to exist in the room, like maybe you might have a rat or something that we'll kill. We'll have a death match with a rat. And then we'll keep evolving this thing from here. So we're thinking about our objects. Let's start with a room object. So we can almost think of this guy as like a node in disguise, right? So this is kind of our graph-based data structure that we're looking at here. And it's a bunch of rooms interconnected to other rooms in some sort of way. And well, we'll talk about these guys here in a second. Okay, so we have a room, and a room is going to have, I think by this thing I said, the title of the room, obvious doors leading out of the room, and other inhabitants. So a room will have a title. It'll have a collection of doors, and it will have a well, okay, we'll come back to that in a second. It'll have a collection of inhabitants. All right, so a title, what kind of animal is this guy going to be? Probably a string. Title of the room going to be a string. What about collection of doors? How many exits does a room have? Well, this room has 2. This room has 2. This room has 1. This room has 1. So how can we represent the collection of exits and why? So, or collection of doors. So how many doors is a room going to have? What do you think the range of doors is going to be?
1 to 4.
Okay. Probably a reasonable assumption for a north, south, east, west. I guess you wanted to have a trap room, you might have 0. If we kind of think about the future of the game, maybe you get stuck in a trap and you get passed into a room, and that room actually has no visible doors, and you got to cast a spell or something like that to get out of the room or something like that. All right, so we need a collection of doors, and we're suggesting we might have 1 to 4 doors. So how do we store this and why? So how do we represent our collection of doors?
Could you represent them as ints?
Well, the number of doors would be an int. A door itself is going to be another object.
Right.
You want to come back to this? We can. Let's go back and let's implement our doors first. Or think about our doors, then we'll come back to this. But this is going to be a collection of door objects. So let's think about a door object. All right, a door object is going to represent our edges here in our graph, right? So a door links 2 rooms together. All right, so A door is probably going to have a direction, and that might be represented as a string. Now we can decide how we want to implement this. Do we want to have this exist as a single door? Or do we want to have a door from here going to the west to this room and a door from here going to the east to this room? We can have two separate doors, or we can have a single door that has two different directions associated with it. Do you have a preference? All right, then I'll just pick. So a room is going to have a direction leading to room A, and I'll have a direction leading to room B. It'll have a room A, it'll have a room B. So that means there exists a single door that connects these two rooms. The door that leads to room, if this is room A here, will be to the west. The room that leads to room B will be to the east. All right, so a single door will have two rooms and two directions associated with it, so we can represent the way we move between those two rooms. Now, by making this decision, we've now locked ourselves into either a future hardship or a, well, here's the issue. We've now said that every single door has to be a two-way door. It's possible to, we might say in our game, it might be possible for there to only be a one-way door. That is, I go from this room to the west, but I can't actually get back. Maybe the door disappears after I've gone through. So we can either represent that as two separate doors or play the game of null values or something like that to say, technically, there's a door from here to this room to the west, but there's not a door leading back. All right, so we can decide how we want to do that, but we've made this decision now that a door is going to keep track of two pieces of information. A direction string for the two directions it goes, and then the destinations for that. All right, so a single object will hold both of those nodes in it. And I think the reason to do it this way is going to be that when we go to create our doors, they will end up being a little simpler to create. But anyway you cut it, we're going to have, I think there'll be some hardships either way, so we just made the decision. Okay, so that's what a door is. Now we have a student. A student's probably going to have a name. That's a string. A student might know about the current room they're in. If you put yourself in the shoes of a student and you're in the computer science department, at any point in time, do you probably know where you are in the department? So you would know where on this map you currently exist. So we're going to say a student knows about the current room. That's going to be a room object. All right, so let's leave it at that for right now. We'll add to it as we get into this. All right, so getting back to this, we've mentioned that for our door objects, so an individual room, like this room right here, has two doors in it. But we don't necessarily know how many doors there's going to be in a room. There could be one door, there could be four doors. So my question is what kind of data structure will we use to hold our collection of door objects and why? What are our options? Well, we could use an array, we can use a linked list, we could do a stack, a queue, a binary tree, a graph. So which one of those might you choose to use for your collection of door objects, and why? What's there needs to be a rationale behind it. Now we're practicing using our data structures.
Array.
You want an array? Okay, tell me why.
Because we know we're only going to need at most 4 doors, and arrays are fast, and you could access the doors by buckets.
Okay. Well, what if you created a 4-bucket array, but you only have 2 doors?
That's a oof.
Is that a problem?
I mean, it's not really a problem. You're just wasting memory.
Okay, but you're not really wasting that much memory, right?
Yeah.
You're looking at it from the perspective that we, even if we say the limit's not 4 doors, if we just start to allowing us to have directions like up and down and jump and, whatever, realistically speaking, we have probably less than or equal to 10 directions, right? If we got really creative. So the most number of exits most number of doors an individual room might have would be something south of 10. Normal cardinal directions, we'd say 4. So even if a certain room only has 1 door, we're only wasting 9 memory addresses, right? Not really the end of the world. Okay, I think that's a reasonable explanation. What would be another option and why? I think we determined we could use arrays and be a little wasteful with memory. We'd have to probably keep track of a count. How many doors does this room have? Something like that. But they would be fast, and we're dealing with a game here. So maybe speed is something somewhat important. So what else could we use? What would be the argument for a linked list? Somebody else. We don't
For
have
that, it could hold like the direction it was going, as well as the room it was going to. And nodes are valuable in that way because each individual one can hold multiple pieces of information.
Okay, well, so we're already going to have that with our door object, right? So our door object is going to be able to hold these multiple pieces of information about the way this door goes, the 2 different directions and the 2 different rooms that it goes to. So whether you call it a door or you call it a node, kind of the same thing. I guess in the context of us learning about graphs here, I'm calling this our door. So this was our edge between 2 of our nodes in our graph. So we have rooms connected to each other through doors, or we have nodes connected to each other through edges. So that's how we'll represent a door itself. But how do we represent a collection of those doors? So we have one suggestion that collection can be represented as an array, where we don't exactly know how many doors we're going to have. We might have 1, we might have 4, we might have 8. But we're going to have a relatively small number of doors in a particular room. So since arrays have the benefit of being fast, we could choose to use an array to hold our collection of door objects and just be a little wasteful with memory. Sometimes, even most of the time, we're probably going to, if we kind of made a guess on average, how many doors does a room have? We'd say 2. Something like that. It might even be 1. Think about the doors in your house, the rooms in your house. Probably most rooms only have 1 door going in and out of the room. All right, so that would be a rationale for using arrays. What would a rationale be for using linked lists to hold our collection of doors? Why might a linked list be better than an array for our collection of doors? So this comes down to us deciding what data structure makes sense and why. Why do we choose it? Picking the right tool for the job. So somebody give me an argument for why a linked list might make sense for our collection of door objects for a read. What are the advantages of a linked list over a array?
That they're memory efficient, or
Okay.
they can store memory without being wasteful with it.
Okay, so we wouldn't waste
But
memory.
they're slower as a result.
Okay, so the idea here is that if we use the linked list, we would always have something that was the exact size for the number of doors a particular room had. If the room had one door, we'll use memory for one door. If the room had 8 doors, we'd use exactly enough memory for 8 doors. Okay, so we won't be wasteful with memory at all. What about the argument of a speed? So you mentioned that linked lists are relatively slow compared to arrays. So if we're making a video game, even though I realize this is a text-based video game, do you think we care more about memory or do we care more about speed?
We care more about memory because text-based is pretty. A text-based game is usually pretty instantaneous unless the text is.
Okay.
So yeah, I think this would be a case where I think you would have more of a better argument for memory. I mean, you could still make the argument for speed, but I feel like memory would be more important in this case.
Okay. I don't think that's an unreasonable position. So that's taking it even at a more granular level of saying, yeah, it's a game. And usually for a game, we might say that speed is probably really important. You're taking it one more step and saying, well, you know what, this is a text-based game. And because of that, maybe memory is more efficient or more important because maybe we're almost putting this in a time period, right? We're saying, okay, it's a text-based game. Maybe this is actually, we're putting ourselves in the shoes of somebody writing this in the 1980s, where maybe memory is pretty important and speed is kind of less important for something like this. Okay, fair enough. I think that I would say it wouldn't be, that's not the direction I would go, but I think your argument is a sound argument for your suggestion. I'm kind of thinking about from the construction of a piece of large software. When we, so even though this is starting off as a text-based game, we start thinking about our modern day, video games. Doesn't matter what game you've played, whether it's Mario or, one of these, first-person shooter, killer games, whatever, or World of Warcraft, whatever the game is. Can't you recognize that there is an underlying logic to that game that is very much a kind of a text-based game that we've now put a nice front end on with, cool animations and good-looking graphics and things like that? That actually is what we're eating with our eyes, right? That's what we're visually enjoying. But under the hood, we have effectively a whole bunch of text-based logic, right? And we're passing information over the network in text, saying this is where this dude is located. That way your client can show the guy that's coming at you over on the screen and you see him moving. So that information is being passed back and forth over and over and over again. All right. So if we're kind of thinking with a modern mindset, let's say, and again, your rationale is perfectly reasonable. So what you said is a correct answer because your rationale matched up to your suggestion. But if we think about it from a modern perspective, we might say that in general, memory is not a problem, and we're making a game, so speed is probably something we want to have a lot of. Even if we might not need maximum speed for this portion of it, we might choose to make this an array for speed. Okay, so let's say we're going to make that decision. So we're going to say an array because we won't waste too much memory and they are faster. All right. Similarly, could we make a similar argument for the inhabitants? Or does that get a little bit more sketch? If we think about let's take it away from the idea of a video game, because at this point we're kind of creating a framework that could be used for this game, but actually what we're describing right now is kind of a virtual collaborative world, a virtual collaborative environment. We don't know what we're going to do in that environment yet. Are we going to be running around and killing rats? Or is this going to be like a virtual chat room, right? Where you have your avatars in there and you're all just sitting there and talking and things like that. We don't know what we're going to do with our virtual space yet. But we can kind of think of, if we're representing, so let's think about this as the department. If we take one of the rooms in the department, the number of exits is going to be relatively small. 1 or 2 doors, 3 doors max, something like that. What about the number of inhabitants? How many people might we have in this room right here? Well, right now, there's probably 0 people in that room. What's the maximum number of people we might have in that room? What do you think? Maybe 25? Something like that, based on the number of seats in the Mac lab. Okay. But now, is that really filling the room? How many people could we really fit in that room if we really explored the space? 40?
Maybe like if they
50?
were standing, like 50, yeah.
70? We start stacking?
If you really want to pack it in as like one of those candy jar things that like you try to guess the candy amount, it would be like probably 150 maybe.
Sure. But the punchline thing here is that now, is it clear, regardless of what number we pick, is it clear that we can fit more inhabitants in a room than it is likely to have number of doors in a room? Okay, so now the number of inhabitants that are in a room, that's going to be something that's probably going to flex often as well. So once we build this room and we put 2 doors in there, is that likely going to change? Is the number of doors in a room gonna shift? Like when you show up to S118B or something like that in the department, is there a different number of doors a couple times a week, or is it pretty much always set in stone? It's a set thing. But what about the number of people in a room? Different classes have different numbers of people. If you show up to the lab at 8 o'clock at night, you might find 4 people in there. If you show up at 3 o'clock in the afternoon, it might be empty. So it's probably going to be much more common for people to come and go from a room than it will be for doors to come and go from a room. So the collection of inhabitants in a room maybe needs to be a little bit more elastic. We're going to want it to shrink and grow and things like that, where certainly we could create an array and say, okay, well, we're going to put a maximum cap of 50 people in a room and just say that's good. But maybe a linked list would make more sense for a room, right? Where we have a collection of inhabitants and that we'd have people leaving and coming and things like that all the time, potentially. So let's go ahead and also add to a rationale for our array up here. Number of doors is unlikely to change very often. Not that you can't put a new door into a room in your house if you're remodeling or something, but it's not something that happens real often. Collection of inhabitants, you might say, this guy should be a linked list, because we really don't know how many inhabitants we will have at any point in time. And that number is likely to change often. Does that make some sense? Okay, now one thing I want us to notice here, and I expect that most of you did not do this, it's kind of the point of the homework assignment. You notice how we've been sitting here for 20 minutes or something like that talking about this, and we haven't written 1 line of code yet. We are planning what we're going to write here. This is the software engineering step minus the collaboration piece of it, where we're going through deciding what's the right tool for the job to build this thing. If you're going to cook a lasagna at home, you don't just dive in and then halfway through realize you don't have one of the ingredients. You make sure you have everything you need to build it before you dive in and start building it. Or at least that would be a reasonable way of doing it, right? All right. So for our room, we decided we're going to hold our title as a string, our collection of doors as an array, and our collection of inhabitants as a linked list. Fair enough? A door, this guy just has 4 pieces, right? It's a couple of strings. These are the directions leading to it, but we've decided that we have a single door that links 2 rooms, rather than there being a door leading from this room to the west, and a door leading from this room to the east. We've decided to have a single door that holds both sides of the equation. So the door leading to this room will be to the west. The door leading to this room will be to the east. So for a door, we're going to have 2 different directions and 2 different rooms. All right, and then we'll have to make sure we keep it straight what direction is related to which room, in terms of, is it the direction leading out of a room, or is it the direction leading to a room? When we write it, we'll just make sure we're clear with that. Otherwise, we might have a situation where we say, well, we take this door to the east to get here, and we take this door to the west to get back over here, because we flip-flopped our directions. All right, so we've added a little bit of complexity there, but once we get into it, I think we can keep it straight using well thought out variable names, that kind of stuff. All right, so that's what a door is. And initially, a student is going to have a name, and they're going to have a current room that they're in. All that make pretty good sense? All right, so now we can start writing this guy. So I'm going to go ahead, I'm going to create doors and students first, because they're pretty straightforward, they're pretty simple, and rooms are built in terms of those things. All right, so for right now, I've called this a collection of inhabitants, just to keep it on par for us right now. We're going to talk about this in terms of a collection of students. As we upgrade our game over the next couple of weeks, we're going to evolve into an inheritance model where we have an idea of something called an inhabitant, where like a student is an inhabitant, but so is like a monster. You know, we might have a dragon that inhabits a room. We might have a rat that inhabits a room. We might have a chair that's tactically an inhabitant in a room. Stuff like that. All right, but for right now, our only inhabitants, we have our little collaborative world here is made up of rooms with doors and people and students running around in it. Okay? So let's create open a folder. And create a folder. Let's see, what should the name of our game be? How about Dungeons and Data Structures? Okay. So we'll go ahead and create a new file in here, and we are going to either do our student or so we have our student HPP. So this guy is going to have our class called student. And we need to have using namespace. Standard, Ninja. And I need to import or include string. I think that'll let me use my string class. All right, so we decided for students, we need a name and we need a current room that they're in. And now, in order to know about rooms, we're going to have to include room.hpp as well. We haven't written it yet, but we're going to need it. Include room.hpp. That guy's probably going to yell at us for a little bit, but that's okay. So we're going to have our private section here. We're going to have a string name. And we're going to have a room, current room. Then we have our public section. And we're going to have our student. And this guy will take in a string name as a parameter. And for right now, let's just leave it at that. Okay. Now, we'll go ahead and we'll open up our, oh, and I'll go ahead and do the, just so we can keep ourselves somewhat sane. With an if and define.
It's all one word.
Oh, if
And
and def like that.
with a hash in front of it, yeah.
Okay. And we're doing this for student, right? Is it student, what, underscore HPP, something like that?
Yep.
Do you want that to be a room pointer or a room?
Probably a room pointer. All right, so if not defined this guy, then we do all this junk, and then we would have the end if. Okay. Does that look right?
And then the define as well. I don't know if
Oh, yeah, now we're defining this stuff. Is it def? Let me just look it up. So I have the model in front of me. Too many different languages floating around. I'll do it in here. Of course. Okay. Found define and why does that not seem very happy? Oh, because we need to put the define after. We have to define student HPP, right? Something like that. All right, so if we have a little hiccup there, we'll come back and patch it up. I'm going to go ahead and I'm going to create my room HPP now as well, so this guy will stop screaming. But I'll create it as kind of an empty husk initially, and then we'll go and fill it in. So we're going to have room.hpp. And I'll steal this top part here. And remember, the reason we're doing this if not defined stuff is so that we can go ahead and include anything that we use in any file and not worry about redefining it. That way we don't have to kind of juggle where we have access to it and where we don't have access to it. So this gives us kind of a convenience. All right, so I'll do that there, and that should make student a little happier. Now he knows about rooms. All right, so now let's go ahead and let's make a door. .hpp. Now, I just want to publicly say here, Clancy, that I was really fumbling over that if not defined there, and the only person who bailed me out was Sarah.
You know, I was looking at it, and then I was about to say something, but Sarah beat me to it, so she could take over my job for the rest of the semester.
You're that quick to hand off your job, but you were trusted.
Aye.
All right. All right, so for door, we decided this guy was going to have a couple of strings and then a couple of rooms that it led to. So let's be careful with our naming conventions here. So we're going to go ahead and we're going to include room.hpp. We're going to need rooms here. We're also going to include string, and we'll do using namespace standard. Oh. All right. Actually, I think that just showed us in the syntax that we're actually supposed to have all this inside of opening and closing curly braces, but it's fine. All right, so for our door, we're going to have private string. Let's call this direction to room A. Steal this line. Direction to room B. Room pointer, room A. Room pointer, room B. So this direction to room A will live inside of room B, leading to room A. That's why we said to room A. And public, we'll have our constructor for door, and this guy will take in a string. Ay, ay, ay. Direction to room A. Then let's take in a room pointer, room A. And then direction to room B and room B. All right, so that'll be our constructor for that guy. So I just kind of grouped our directions next to our room, so we'll know that, for instance, when we go and build this guy, if he's room A, we'll have a direction to the west leading to room A, a direction to the east leading to room B, like that. That's the way we'll design this. All right, so that's our constructor for our door. All right, so that's student and door and our placeholder for room. So room is going to need to include door HPP. It's going to need to include string. it's going to need to include student HPP. Because rooms are going to have a title, it's a string, going to have a collection of door objects, and then it's going to have a collection of students. So our collection of door objects we'll have our private variable here of a string title. I need to using namespace. What are you not happy about?
Is it string.h? I don't know. Like sometimes one works for me and the other doesn't, but I don't know if that would work.
It should just be string since it's in a namespace, but I guess we'll stumble upon it eventually. It could just be a Visual Studio Code thing.
Nothing else, you could include IO stream, and that should fix it.
We might actually need IO stream anyways for a string. Well, I'm going to leave that out for right now. We'll wait for the error and then we'll fix it up. All right, so we're going to have a string title. What else are we going to have? We're going to have an array of doors. Now, our array of doors, we've decided what? Do we want to just pick 10 as our maximum number of doors? So we're going to have a door pointer let's call this collection of doors, and this guy will have up to 10 of those guys. Now, because I have up to 10 of those guys, I also am going to need to have a count for the number of doors we actually currently have. Because I've given myself a big enough array to hold 10 of those doors, but I don't actually have 10 doors in there yet. So I'm going to say int number, let's call it current number of doors. I think we can actually default that guy to 0 here in the header. We could also do it in the constructor. I'll actually do it in the constructors, put it all in one place. All right. Then we're going to need a linked list of what are we doing? We're doing a linked list of students. So let's go ahead and look up C++ linked list. And I think there's one built into STD. Otherwise, if we can't find a quick use for one, we'll just write it. Yeah, they're writing it with, I'm sure there's one built in, but we'll just write it. It'd be good practice. All right, so we're going to need to have a linked list of objects. Well, we'll do a linked list of students here because we might want those to work a little different, and we can always modify it later. So we're going to have our nodes will be, actually, let's build it with generic nodes where the payload is a student. I think that'll make reasonable sense. All right, so we're going to call this guy a linked list of students. .hpp, and we'll do our same we call it students. Yep. And then we'll have our diff. We'll have our class linked list of students. All right, and while we're at it, let's go ahead and create our node. Call this guy a student node. .hpp. All right. Our student node will have a payload, which is going to be a student object. So we're going to need to include student HPP and we'll say node pointer payload. Oh, sorry. I need to call this a student pointer. And then I'm going to have a student node pointer next node. All right, and we're going to keep this guy simple because we can just add front or add end, remove front, or we can add front, remove front. Maybe that's going to be the easiest. Doesn't really matter how they're stored. We just need to have them stored in an expandable way. We are going to need to be able to, so we can always add them to the front. I think that's reasonable. But when we remove, we need to be able to remove at a particular index because we need to find them at that index. Okay, so we'll get to that. Right now we are going to have to remove them. So we'll just keep trucking. So public, we have our constructor for this guy. So it's going to be a student node. Student node is going to take in a student payload. All right, and then we'll have a void add front. And this guy will take a, actually this is our student node on our linked list yet. All right, so that's going to be our student node. We'll just leave it at that for right now. We need to have a set payload and a set next node. So void set. We don't need to set the payload because we're taking that as constructor, so we need to have a set next node. And this guy will take in a student node pointer as a parameter. Then we need to have a student pointer get payload. and a student node pointer get next node. All right, so that's what that guy needs to be able to give us for our student node. So we build it with a payload. We can set the next node, as that might change. Payload won't change. And then we gave ourselves the ability to get the payload and get the next node. We haven't implemented it yet, but this is all at the header level. All right, then we have our linked list of students, this guy. So we're going to need to keep track of where the front of the list is. So we're going to need to include student node HPP. So we'll have a private student node pointer called head. Then also let's have a count. Be handy to know how many people are in the list at any particular point in time. All right, and then we're going to have add front. Well, we did our constructor for this guy too. So we have our linked list of students. List of students. Sure, that would have been one of those haunting bugs. Linked list of students. All right. So we'll have our constructor for this guy. He'll take nothing as a parameter and initialize our linked list. Then we'll have a void at front. And this guy will take in a student pointer as a parameter. Then we'll have a void get at index, take in an index, and this guy will return a student pointer. And then we want to have a student pointer remove at index, int index, and he'll take in a index and return the student pointer that we're removing. So this will give us a structure that we can always add people to the front of. We can go and get something at an index, and then we can also remove something at an index. We might want to go and add some other things, like maybe find something like that, that will look for a student in there. In fact, we can even do that. If we have int index of, and this guy is going to take in a student pointer s, and he'll return the place in this linked list where that guy lives, or -1. If it's not in there, returns index, or -1 if not found. Something along those lines. All right, so that's what our linked list will be. It's going to be a collection of students, or student nodes, where student nodes hold the student and know about the next node, so on and so forth. All right, so let's go and write our linked list. Well, let's actually implement our student node guy real quick. So I'll steal these methods, and we'll go ahead and do our student node CPP. And we will include student node HPP. Go ahead and put these pieces in here. All right, So when we create a student node, we're going to set this guy's payload equal to the payload, and this guy's next node equal to null. Set next node is going to set this guy's next node equal to n. Get payload will return this guy's payload. Get next node will return this guy's next node. All right, so that is our student node. Now our linked list, we will steal these guys and we'll create linked list of students.cpp. And this guy will include linked list of students HPP. Ooh. This one, Ninja. All right, and then we'll get this. All right, so linked list of students. We go back and look at, oh, this guy takes in nothing, and we're going to set our head and our count, head to 0, count to 0. We'll set this head equal to null. There's nothing in our linked list right now, which means that we currently have a count also of 0. All right, add front. We'll ask the question if we currently have a front. So any way you cut it, we're going to create a new student. So I'll create a student pointer S. Actually, we're getting a student pointer out of this guy. So we're going to create a new student node. Student node pointer SN is equal to a new student node. And our constructor for student node takes in just the student payload, and it does the work for us. And that guy is to set the payload and set the next node to nothing. We'll pass this guy S. So now we have our student node. We're going to ask the question if not this head. If there is not currently something at the front of the list, then we'll say this head is equal to SN. Else, we need to connect it up. Regardless, we'll say this count plus plus. Okay, so to hook it up, we need to make our new guy, SN, set next node to head. We make him point to the same place head points to, and then we make head point to SN. And that will add it to the front. And then whether he became the first front or he's the new front, we just incremented our count by 1. All right, get it index. We can assume that they're giving us a, actually, we can we can do a little error checking now since we're writing a game and we want to be a little careful with this. So we'll say if index is greater than count minus 1, or index is less than zero, will return a 0. So this says if they give us a bad index, return null. Otherwise, if I'm still kicking, and you didn't have to put this in an else because you returned up there, so you could have just had it down here, but we'll put it in an else to be nice and complete. All right, so otherwise we need to zip to that index. So we'll say we'll say student node. Do I already have that here? I do. We'll call this guy kernode. We'll start this off at head. We'll say for int I is equal to 0. I is less than index. I plus plus. Kernode is equal to kernode get next node. And then we'll return kernode get payload. All right, so we'll either return null if they give us a bad index, or we'll start at the beginning, zip up to the index, jumping kernode to his own next node over and over again. Finally, once we're at the right index, we will return kernode's payload as a student pointer. All right, so that's our get at index. Remove at index means we need to get to the place that is at a particular index. We actually want to get to the guy right before him. So we can ask the specialized question, if index is equal to 0, we're removing from the front, right? So if we're removing from the front, then we're going to, well, here, let's just say remove from front, else if index is equal to count minus 1, we're removing from the end, else we're remove from the middle. Okay, so remove from the front, any way you cut it, we're going to have a variable that's going to be the guy we want to remove. So we're going to have our student pointer. And actually what we can do is we can have some more error checking in here and say, if this count is equal to 0, or if not, this head return 0. Is the list empty? The list is empty, then they gave us an illegal index, or index less than 0, or index greater than this count minus 1. All right, so if they gave us a bad request for any, is list empty or is index out of range? So it's either the empty list, or they gave us a negative number, or they gave us a too big of a number. We'll go ahead and return null. Otherwise, they gave us reasonable stuff. So we'll go ahead and throw this code in here. All right, so if index is equal to 0, we're removing from the front. So what we need to do is, any way you cut it, we're going to have the guy we're going to return, which is going to be a student pointer. So we have our student pointer. Let's call this student to return, because we are removing an index, but we're going to spit out what we removed as well. So we'll say student to return is equal to this head. Then we'll say this head is equal to this head get next node. So we'll remember the head of the list. We'll update the head of the list to be his own next node. At the very end, we will return student to return. So one way or another, that variable is going to get set in one of these three parts of our if structure. So it'll either be the front, or he's going to be the end. Now, if we kept track of tail, we could have gotten there pretty easily, but not a big deal. So we'll go ahead and give ourselves a node pointer. It's not a node, it's a student node. Student node pointer cur node. We'll start this guy off at this dot head. We want to zip all the way to the end, but we actually want to go to the guy right before the end. We know if we're in this else if that we're dealing with at least a to list, because we know they give us a legitimate value, and we know it wasn't the front. So the front and the end are the same if we're dealing with a one list. So if we're in this else if, that means it wasn't the front, so we're dealing with at least a to list, which means that we can get to the guy right before the end. So we want to go all the way up to, but not including the last guy. So we're going to say for int I is equal to 0, I is less than this count minus 2. Actually, it'll be minus 1. Will get us to the actual guy right before. Because less than count will get us the last guy. Less than count minus 1 will get us to the guy before the last guy. I plus plus. And we'll say cur node is equal to cur node. Get next node. So we'll run him down the list. So this guy positions cur node to the guy before the last guy. So then we will set student to return equal to cur node get payload. And actually, with that in mind, this dot head, this isn't quite right yet. This guy needs to be get payload. So we want the student that's at the student node at the head. Similar here, we want the student that lives at the cur node, which is the guy right before the end. But actually, we're removing the end, not the guy right before the end. So we actually want get next node get payload. So cur node is the guy right before the last guy. Cur node.get next node is the last guy. We want the last guy to give us his payload because that's the guy we're going to return. So now we're going to go ahead and say, we want to be memory efficient. We'll say student node pointer node to delete is equal to cur node get next node. Then we'll say cur node set next node to null. Then we'll say delete node to delete. Okay, so the student we want to return is the actual last guy. So this is, we have the guy before the last guy here. Then the last guy is the guy we want to delete. We'll go ahead and set the second to last guy's next node equal to null, making him the new last guy. And then we'll delete that variable that is going away. But this is after we had preserved the student from that node, because we're going to return him here at the end. Okay. Otherwise, we need to remove at the middle. Okay. So for your homework, now for starters, if you happen to do yours the same way I wrote mine here, feel free to just submit it. I'm going to doubt that most of you did it that way. You probably, so one thing I want us to get out of today's class is this idea that before we ever started writing the code, is we started thinking about what data structures did we need to represent the different parts of our project here. We just don't dive in and start doing it. All right, so update your code to be the same solution as we had for this class, but using the linked lists for our students. So you'll have to finish our implementation of linked list, as well as our, and debug it if we have any issues in there, as well as our array representation for doors. We went through the mindset of this and we decided we'd store doors as arrays, we'd store students as linked lists. So modify your current solution with that. And I'll give you this code as a starting point on GitHub. So make sense what I'm asking you to do? Same homework as you had for today, but using my approach to it with linked lists and arrays. And I'll give you mine as a starting point. Go ahead.
I was just wondering, with the data structures, why didn't you build like a graph or a map data structure? Like,
Good.
Okay,
rooms and edges, or nodes and edges. So
Okay.
our graph is made up of rooms and doors.
Okay.
Yep. So that's actually the point of what we're doing with this kind of project, is we're moving ourselves away from the idea that data structures have set names. All semester long, we've been writing things that are like stacks, like Towers of Hanoi. Our tower was like a stack, but behaved a little differently. Shunting yard, we had our op stack, was like a stack, but it had some rules associated with it. So in this case, we have our map of our rooms, if you will. So rooms and doors, which are like a map, but they're going to have some differences to them potentially. When we take an edge, we might decide we want to need a key or something like that to open a door, or that kind of stuff. So we're using the underlying data structure, but we're writing it for what we actually need here. All right, so consider what we have as this representation so far. We have a graph made up of rooms and doors. So that's our nodes and edges. We have a linked list of students, and we have an array of doors. So we have 3 different data structures being represented in terms of collection data structures. And then we actually have 3 different additional data structures, one for a room, one for a door, one for a student, that are holding information about these particular players in our particular actors in our game. So we actually have 6 data structures present here, even though none of them, actually besides the linked list, we do have something that has the word linked list in it. So 5 of them don't match names of the traditional data structures, even though they are in the spirit of those underlying data structures. Does that make sense?
Yeah, that helps. Thank you.
All right, any other questions, comments, concerns, bribes? All right, I'll get this up on GitHub. I'll compile it real quick and just make sure there's no crazy stupid errors. I don't want to give you like horribly bad code, but you know, you'll want to test it to make sure it works before you go on. But this has forced us to have that mentality of how do we design this and now finish the implementation. I will see everybody on Thursday.
I think GitHub's down, just so you know.
Okay. And I'll keep the recording going for a few minutes as I go and debug that in case you're interested or you want to hang out. Doesn't matter to me. I'll just keep the recording going while I make sure this guy comes close to compiling. I'll set that equal to null. What do I call it? Dungeons and data structures. Room has not been declared in door HPP. Or let's name it type. Doesn't like my rooms very much. Let's see why not.
I think I had a similar issue.
I don't have a constructor for this guy yet.
Yeah.
Oh, we actually didn't even write room yet. So this room will take in a title. And then we'll write room CPP. It looks like I'm gonna have to create the CPPs for all those. All right, so this is include room HPP. Just double check something here real quick. Okay, I'll have to expedite this because I have a student I'm meeting with here in a few minutes. What room are we in? Are we in 154? What room are we in? We're not. So I'll have to finish debugging this because he's going to be trying to get into that room in a minute. So I'll finish this up and get it uploaded to GitHub. I think all I'm going to have to do is just create my CPPs for room and student and door and give the constructors just so they can exist Because if you look at the compile thing here, it's having a major issue with rooms not being a thing. And I think after that, it should be fairly clean with a little bug here and there. All right, but I'll get that up by, I think this next meeting should only take maybe 15, 20 minutes. So I'll get it up after that. All right.
Sounds
All right.
good.
Talk to you guys later.
See ya.
Bye-bye.